Hello friends, today we are going to start a series of lectures on thermal physics. Thermal physics is the combined study of thermodynamics, statical mechanics and kinetic theory. This umbrella subject is typically designed for physics students and functions to provide a general introduction to each of three core heat related subjects. Thermal physics, generally speaking, is the study of the statical nature of physical systems from an energetic perspective. Starting with the basics of heat and temperature, thermal physics analyzes the first law of thermodynamics and second law of thermodynamics from the statical perspective in terms of the number of microstates corresponding to a given microstate. In addition, the concept of entropy is studied via quantum theory. Other topics studied in thermal physics include chemical potential, the quantum nature of an ideal gas, chemical equilibrium, phase equilibrium, entropy at absolute zero, and transport process as mean free path, viscosity and conduction. Thermodynamics. One of the principal branches of physics and engineering is thermodynamics, which is the study and application of thermal energy, often called the internal energy of systems. One of the central concepts of thermodynamics is temperature. Since childhood, you have been developing a working knowledge of thermal energy and temperature. For example, you know you should be cautious with hot foods and hot utensils, and you know how to store perishable foods in refrigerators. You also know how to control the temperature inside a car and how to protect yourself from wind chill and heat stroke. Examples of how thermodynamics figures into everyday engineering and science are countless. In this lecture, we shall be discussing some basic concepts such as system, state, state postulate. We shall also be discussing equilibrium and process, but we start with application areas of thermodynamics. All activities in nature involve some interaction between energy and matter. Thus, it is hard to imagine an area that does not relate to thermodynamics in some manner. Therefore, developing a good understanding of basic principles of thermodynamics has long been an essential part of engineering education. Thermodynamics is commonly encountered in many engineering systems and other aspects of life, and one does not need to go very far to see some applications area of it. In fact, one does not need to go anywhere. The heart is constantly pumping blood to all parts of human body. Various energy conversions occur in trillions of body cells, and the body heat generated is constantly rejected to the environment. The human comfort is closely tied to the rate of this metabolic heat rejection. We try to control this heat transfer rate by adjusting our clothing to the environmental conditions. Other applications of thermodynamics are right where one lives. An ordinary house is, in some respect, an exhibition hall filled with wonders of thermodynamics. Many ordinary household utensils and appliances are designed in whole or in part by using the principles of thermodynamics. Some examples include the electric or gas range, the heating and air conditioning systems, the refrigerator, the pressure cooker, the water heater, the shower, the iron, and even the computer and television. The energy efficient home that you may be living in, for example, is designed on the basis of minimizing heat loss in winter and heat gain in summer. The size, location, and the power input of the fan of your computer is also selected after an analysis that involves thermodynamics. Systems. A system is defined as a quantity of matter or a region in space chosen for study. The mass or a region outside the system is called the surroundings. The real or imaginary surface that separates the system from its surroundings is called the boundary. The boundary of a system can be fixed or movable. Note that the boundary is the contact surface shared by both the system and the surroundings. Mathematically speaking, the boundary has zero thickness and thus it can neither contain any mass nor occupy any volume in space. Systems may be considered to be closed or open depending on whether a fixed mass or a fixed volume in space is chosen for study. A closed system, also known as a control mass, consists of a fixed amount of mass and no mass can cross its boundary. That is, no mass can enter or leave a closed system, but energy in the form of heat or work can cross the boundary, and the volume of a closed system does not have to be fixed. If, as a special case, even energy is not allowed to cross the boundary, that system is called an isolated system. Control volumes. Consider the piston cylinder device shown here. Let us say that we would like to find out what happens to the enclosed gas when it is heated. Since we are focusing our attention on the gas, it is our system. The inner surfaces of the piston and the cylinder form the boundary, and since no mass is crossing this boundary, it is a closed system. Notice that energy may cross the boundary and part of the boundary may move. Everything outside the gas, including the piston and the cylinder, is the surroundings. As an open system or a control volume, as it is often called, it is properly selected region in space. It usually encloses a device that involves mass flow such as a compressor, turbine or nozzle. Flow through these devices is best studied by selecting the region within the devices as the control volume. Both mass and energy can cross the boundary of a control volume. A large number of engineering problems involve mass flow in and out of the system and therefore are modeled as control volumes. A water heater, a car radiator, a turbine and a compressor all involve mass flow and should be analyzed as control volumes, that is open systems. If we were to analyze the flow of air through a nozzle, for example, a good choice for the control volume would be the region within the nozzle. The boundaries of a control volume are called a control surface and they can be real or imaginary. In case of a nozzle, the inner surface of the nozzle forms the real part of the boundary and the entrance and exit areas form the imaginary part, since there are no physical surfaces there. A control volume can be fixed in size and shape, as in the case of a nozzle, or it may involve a moving boundary. Most control volumes, however, have fixed boundaries and thus do not involve any moving boundaries. A control volume can also involve heat and work interactions, just as a closed system, in addition to mass interaction. As an example of an open system, consider the water heater as shown here. Let us say that we would like to determine how much heat we must transfer to the water in the tank in order to supply a steady stream of hot water. Since hot water will leave the tank and be replaced by cold water, it is not convenient to choose a fixed mass as our system for the analysis. Instead, we can concentrate our attention on the volume formed by the interior surfaces of the tank and consider the hot and cold water streams as mass leaving and entering the control volume. The interior surfaces of the tank form the control surface for this case, and mass is crossing the control surface at two locations. A control volume can involve fixed, moving, real and imaginary boundaries. In an engineering analysis, the system under study must be defined carefully. In most cases, the system investigated is quite simple and obvious, and defining the system may seem like a tedious and unnecessary task. In other cases, however, the system under study may be rather involved, and a proper choice of the system may greatly simplify the analysis. State and equilibrium. Consider a system not undergoing any change. At this point, all the properties can be measured or calculated throughout the entire system, which gives us a set of properties that completely describes the condition or the state of the system. At a given state, all the properties of a system have fixed values. If the value of even one property changes, the state will change to a different one. As shown in this figure, a system is shown at two different states. Thermodynamics deals with equilibrium states. The word equilibrium implies a state of balance. In an equilibrium state, there are no unbalanced potentials or driving forces within the system. A system in equilibrium experiences no changes when it is isolated from its surroundings. There are many types of equilibrium, and a system is not in thermodynamic equilibrium unless the condition of all the relevant types of equilibrium are satisfied. For example, a system is in thermal equilibrium if the temperature is the same throughout the entire system, that is, the system involves no temperature differential, which is the driving force for the heat flow. Mechanical and chemical equilibrium. Mechanical equilibrium is related to pressure, and a system is in mechanical equilibrium if there is no change in pressure at any point of the system with time. However, the pressure may vary within the system with elevation as a result of gravitational effect. For example, the higher pressure at a bottom layer is balanced by the extra weight it must carry, and therefore, there is no imbalance of force. The variation of pressure as a result of gravity in most thermodynamic systems is relatively small and usually disregarded. If a system involves two phases, it is in phase equilibrium when the mass of each phase reaches an equilibrium level and stays there. Finally, a system is in chemical equilibrium if its chemical composition does not change with time, that is, no chemical reactions occur. A system will not be in equilibrium unless all the relevant equilibrium criteria are satisfied. The state postulate. As noted earlier, the state of a system is described by its properties, but we know from experience that we do not need to specify all the properties in order to fix a state. Once a sufficient number of properties are specified, the rest of the properties assume certain values automatically. That is, Specifying a certain number of properties is sufficient to fix a state. The number of properties required to fix the state of a system is given by the state postulate. The state of a simple compressible system is completely specified by two independent intensive properties. A system is called a simple compressible system in the absence of electrical, magnetic, gravitational, motion and surface tension effects. These effects are due to external force fields and are negligible for most engineering problems. Otherwise, an additional property needs to be specified for each effect that is significant. If the gravitational effects are to be considered, for example, the elevation z needs to be specified in addition to the two properties necessary to fix the state. The state postulate requires that the two properties specified be independent to fix the state. Two properties are independent if one property can be varied while the other one is held constant. Temperature and specific volume, for example, are always independent properties, and together they can fix the state of a simple compressible system. Temperature and pressure, however, are independent properties for single phase systems. At sea level, that is P is equal to 1 atmosphere, water boils at 100 degrees centigrade, but on a mountain top where the pressure is lower, water boils at a lower temperature, that is T is equal to F into P during a phase change process. Thus, temperature and pressure are not sufficient to fix the state of a two-phase system. We shall be discussing phase change processes in detail in further lectures. Any change that a system undergoes from one equilibrium state to another is called a process, and the series of states through which a system passes during a process is called the path of the process. To describe a process completely, one should specify the initial and final states of the process, as well as the path it follows and the interactions with the surroundings. When a process proceeds in such a manner that the system remains infinitesimally close to an equilibrium state at all times, it is called a quasi-static or quasi-equilibrium process. A quasi-equilibrium process can be viewed as a sufficiently slow process that allows the system to adjust itself internally so that properties in one part of the system do not change any faster than those at other parts. As shown in figure, when a gas in a piston cylinder device is compressed suddenly, the molecules near the face of the piston will not have enough time to escape, and they will have to pile up in a small region in front of the piston, thus creating a high pressure region there. Because of this pressure difference, the system can no longer be said to be in equilibrium, and this makes the entire process non-quasi-equilibrium. However, if the piston is moved slowly, the molecules will have sufficient time to redistribute, and there will not be a molecule pileup in front of the piston. As a result, the pressure inside the cylinder will always be nearly uniform and will rise at the same rate at all locations. Since equilibrium is maintained at all times, this is a quasi-equilibrium process. It should be pointed out that a quasi-equilibrium process is an idealized process and is not a true representation of an actual process, but many actual processes closely approximate it, and they can be modeled as quasi-equilibrium with negligible error. Engineers are interested in quasi-equilibrium processes for two reasons. First, they are easy to analyze. Second, work-producing devices deliver the most work when they operate on quasi-equilibrium process. Therefore, quasi-equilibrium processes serve as standards to which actual processes can be compared. Process diagrams plotted by employing thermodynamic properties as coordinates are very useful in visualizing the process. Some common properties that are used as coordinates are temperature T, pressure P and volume V or specific volume V. Figure shows the PV diagram of a compression process of a gas. Note that the process path indicates a series of equilibrium states through which the system passes during a process and has significance for quasi-equilibrium processes only. For non-quasi-equilibrium processes, we are not able to characterize the entire system by a single state, and thus we cannot speak of a process path for a system as a whole. A non-quasi-equilibrium process is denoted by a dashed line between the initial and final states instead of a solid line. So friends, here we come to the end of our discussion in this lecture, and therefore we sum up. Thermodynamics is the science that primarily deals with energy. A system of fixed mass is called a closed system or control mass. A system that involves mass transfer across its boundaries is called an open system or control volume. A system is said to be in thermodynamic equilibrium if it maintains thermal, mechanical, phase and chemical equilibrium. Any change from one state to another is called a process. A process with identical end states is called a cycle. During a quasi-static or quasi-equilibrium process, the system remains practically in equilibrium at all times. So that is it for today. In the next lecture, we shall be discussing about temperature and zeroth law of thermodynamics. Thank you very much.